Hi folks, in this example we're going to be looking at finding the intervals of continuity for a given function and classifying the discontinuities if there are any. So remember, discontinuities are going to happen at points that aren't in the domain. So let's take a look here at our first function. F of x is x squared minus x minus 6 over x squared minus 9. So this is a rational function. We know it's going to be continuous on its domain, but let's take a look at points not in the domain. So once again, we have a 0, or we have the potential for a 0 in the denominator. So we'll set the denominator equal to 0. And we get two places where the function's undefined, plus or minus 3. So now we're going to use limits to analyze what's going on near these values. So let's check out limit as x goes to negative 3 of x squared minus x minus 6 over x squared minus 9. First thing we try is direct substitution to help us figure out what we're in for here. If we plug in negative 3, in the numerator we'd get a negative 3 squared, which is a 9, minus a negative 3, which would be plus a 3, minus 6. In the denominator we get, of course, a 0. So we're getting a non-zero number over 0 here, 6 over 0. So we know right away that this limit does not exist, which means we're going to have some kind of unbounded behavior, which means we're going to have a infinite discontinuity. In other words, a non-removable. So we could say non-removable, infinite discontinuity. Now, if we wanted to be more precise about the unboundedness, we're going to have to take a look at this function. We can simplify it. Well, we can try to simplify it. So the numerator we can factor as an x minus a 3 times an x plus a 2 divided by x minus a 3 times x plus a 3. Since we're coming into negative 3, we can go ahead and cancel out the x minus 3's, and we can look at what's left. So if we come into negative 3 from the left, well, negative 3 plus 2, that's going to be roughly a negative 1 in the numerator. And in the denominator, we're plugging in things a little less than negative 3. So like negative 3 point something. This is going to be a small but negative number down here, which is going to turn into a big positive. So that tells us that the limit as x goes to negative 3 from the left of the f of x is going to be infinity. And if we look at what's going on the other side, negative 3 from the right, well, the numerator is still going to negative 1, but the denominator now is going to be a small positive. That's going to go to a big in absolute value, negative, and so that limit would be negative infinity. Okay. So on the graph of the function near negative 3, we do get a vertical asymptote there, so that's a non-removable infinite discontinuity, as we had said. But now we know a little bit better what's going on there. Coming in from the left, the function should skyrocket, and coming in from the right, it should be heading down the other way. So once again, x equals -3, non-removable, infinite discontinuity. Moreover, we have a vertical asymptote, x equals -3. So now let's look near x equals 3. Once again, we try direct substitution to see what we're in for. And here, when you plug in 3 in the numerator, we get a 3 squared, which is a 9, minus 3, minus 6. In the denominator, we get a 3 squared, which is 9, minus 9. So we do get that 0 in the denominator, but we also get a 0 in the numerator. And in fact, in the last limit, we can still do the same algebra to simplify the function. So we can simplify things down to the x plus 2 over x plus 3. And I can use direct substitution here to get 5/6. So we have a removable discontinuity here. We have a hole at 3, 5/6. So if I wanted to, I could define my function as follows. I could define my function as it was given to us, x squared minus x minus 6 over x squared minus 9 for x not equal to 3. And then when x equals 3, I can define the function as just being 5/6, essentially plugging the hole there in the graph. So that'll do it for the first example. We have discontinuities at x equals -3 and 3. These are our discontinuities. So the intervals of continuity are going to be everything except those two values. So the interval of continuity is going to be -infinity to -3, along with -3 to 3, along with 3 to infinity. So on these individual intervals, the function's continuous. The graph is a nice connected curve. Second example here, we've got g of x equals x squared minus 25 in absolute value divided by x minus 5. Now once again, the function here is going to be continuous. We've got the absolute value, which is continuous, and we're combining that with quadratic functions and linear functions. So this will be continuous on its domain. So I have to look at where am I going to get in trouble here with the domain. Once again, we have a fraction. We're going to set that denominator equal to 0. And so x equals 5 is where we're going to have a discontinuity. So the question is, what kind of discontinuity are we going to have? So we need to look at the limit. So once again, we go back to direct substitution. I plug 5 into it. I'm going to get the absolute value of 5 squared minus 25 over 5 minus 5. So sure enough, I get that 0 in the denominator, but I also get a 0 in the numerator. So we have an indeterminate form here. So that means that there's a chance we might be able to get this thing to simplify out for us. So let's take a look at the function and try to simplify it. So inside the absolute value, I've got that x squared minus 25. So we can factor that down into an x minus 5 times an x plus 5. And using properties of absolute values, absolute value works well with multiplication. Absolute value x minus 5 times absolute value of x plus 5 all over x minus 5. And let's see which of these absolute values we can simplify here. I know that x is getting really close to 5. So that means the x plus 5 is going to be a positive number. So that means I don't really need the absolute values around the x plus 5. So I can go ahead and drop those. But near x equals 5, I've got to be careful because that's where this absolute value is going to change. If x comes into 5 from the left, I'm plugging in numbers a little less than 5. So that means what's inside here is going to be a negative number. So the absolute value would take the opposite of that to make it a positive number. So as x comes into 5 from the left, the absolute value of x minus 5 would be the opposite of x minus 5. Whereas if I come into 5 from the right, I'm plugging in numbers a little greater than 5. So x minus 5 would be a positive number, and the absolute value would leave that quantity the same. So since I have two different simplifications for the absolute value, I've got to bust this limit up into the two different directions. So as I come into 5 from the left, I'm going to replace the absolute value of x minus 5 with the opposite of the quantity x minus 5. I still have the x plus 5 factor from before, and I've got the x minus 5 factor in the denominator. And I can cancel that out. Now use direct substitution. I'm going to have minus quantity 5 plus 5, or minus 10. Coming into 5 from the right, the absolute value of x minus 5 is x minus 5. So divide the x minus 5 there, cancels out, and I can direct sub, plugging the 5 in to get a 5 plus 5, which is a positive 10. And so if I look at what's going on the graph here at 5, coming in from the left, I'm down here at negative 10. Coming into the right, I'm up here at positive 10. And in fact, you might recognize this function. This was one of the very first functions we analyzed on the first day of class. And so we have a non-removable jump discontinuity here. It's not an infinite discontinuity, it's a jump discontinuity. The limits are finite values, but they don't match. So the limit doesn't exist, which means it's non-removable. The one discontinuity, so the discontinuity was at x equals 5. And so the interval of continuity then is going to be everything up to 5, along with everything from 5 off to infinity. Our last example here, h of x equals the square root of 16 minus x squared. Once again, as far as domain issues here, we just really need to make sure that 16 minus x squared is bigger than or equal to 0. Or in other words, that minus x squared is greater than or equal to minus 16. Or that x squared is less than or equal to 16. Or the square root of x squared is less than or equal to the square root of 16. The absolute value of x is less than or equal to 4, or x is between negative 4 and 4. And as long as x is between negative 4 and 4, I'm not going to have any kind of discontinuities. Now the question is, how do I write my interval of continuity here? Can I write it as -4 to 4, do I include the -4 and the 4? And the answer here is yes, we do, because remember, when you include an endpoint on an interval, you're sort of making a statement about continuity from the left or from the right. So if I look at this function, it ends up being a semicircle. So it looks like this. And you can come into -4 from the left, and it'll be continuous. And you can come into -4 from the right, and it'll be continuous. Or you could come into 4 from the left, and it would be continuous. So since the limit as x goes to -4 from the right of 16 minus x squared is 0, which is the function value at -4, and the limit as x comes into 4 from the left of the square root of 16 minus x squared is 0, which is f of 4, we can write the interval of continuity using those brackets. The bracket here corresponds to continuity from the right, and the bracket here corresponds to continuity from the left. So that'll do it for that example.